This is an introduction to part N, which deals with waves. We'll be studying string waves, waves on violin strings, guitar strings, piano wires, and then later sound waves. I begin by discussing string waves. I show a wall. Connected to the wall is a wire or string or rope, and something is pulling on it to the left to give it a tension. I show the same wall once again, a string, the left end of which is under tension, a pull to the left, and an up and a down arrow indicating some agent, an oscillator, has shaken this end of the string, and it will propagate to the right, headed toward the wall. Let M be the mass of the string and L its length, and define a property called the mass per length, symbolized as mu, lowercase Greek letter mu for M. It's the mass per length M over L. Without proof, I state that the speed of that pulse as it travels to the right is that square root equation, the square root of the tension in the string divided by the mass per length mu. Consider this example. The mass of our string is 2/10 of a kilogram, its length is 1/2 of a meter, and the tension in the string is 50 newtons. What is the speed of a pulse set in motion on this string? Well, from the square root equation, we have inside the radical sign, tension 50 newtons, and downstairs a ratio M over L. Final result for the speed of that pulse, it's 11.18 meters per second. Now, if we were to shake the wire more than once, twice for example, we'd have 2 pulses moving down the wire to the right, or 3, or 4, or 5, or 6. And then you'd have a train of pulses, a succession of pulses. F stands for the frequency of the wave, and it's the number of oscillations made per second by the agent at that end of the string that's shaking it. The units that are standard international for the frequency of a wave are reciprocal seconds, or per second. But that's not the unit we prefer to use. Instead, we call one reciprocal second a hertz. 1 hertz is what is equivalent to a reciprocal second. I show then that train of pulses that I spoke of. This end of the string was being oscillated at a rate of F cycles per second, or oscillations per second. The distance between consecutive peaks, between consecutive maxima, is the wavelength lambda. That's the Greek letter lambda, lowercase l, reminds you of length. Lambda is also the distance between consecutive valleys or consecutive minima. Very important equation is in this red box. It states that for a particular system where the speed of the pulses and therefore the speed of the wave is fixed, which it will be as soon as the tension is chosen and as soon as the mass per length is chosen, then there's only one speed v, but there can be multiple different f's depending upon what your choice is for the number of times per second you shake that into the string. The product of lambda and f is the same number for all values of f or all values of lambda. Notice that lambda f is equal to this number that does not change from one shaking frequency to the next. The product of lambda and f does not change. It's always the same number. So for example, when the frequency of oscillation, the shaking frequency, is large, lambda will have to be small, and vice versa. When f is small, lambda will be large, in order that for all situations the product of lambda and f is the same number, which is the speed of the wave. Let's look at a final example in this introduction. Suppose in the first instance the speed of our wave is 3 meters per second. We're contemplating negotiating for a different speed. In this first case, V1 is 3.0 meters per second, and we're told that the tension in the string is 40 newtons. Now let's imagine we have the capability of adjusting the tension, which we can imagine that we do. we asked the question, what would have to be the new tension, T2, in the second case, in order that the new speed, V2, be 7 meters per second? Well, we cleverly form a ratio of V1 and V2, written like this, using the square rooting equation. This ratio may be simplified by noting that you have a mu, it's the same in the numerator as in the denominator, and so the mu's cancel out of that ratio. And what you have is just the ratio of the tension square root. Now, we have the ratio of the v's equals the ratio of the t square rooted. Substitute for v1, which is 3, for v2 is 7. 3/7 is equal to 40 over t2 to the 1/2 power. I won't bother with the algebra. I'll just report the final answer. The tension that would be required in order to have a new wave speed of 7 meters per second is rounded off to the nearest whole newton, 218 newtons.